Section 7.3, the exponential function. All right, let's recall how an exponential function looks like. Okay, remember, it's the exponent we enter into e. The natural e is approximately 2.72. So if we have -1, that means it's 1 over e. So there's your -1 for the x, and there's your y value. E to the 0 is 1, so there's that point. E to the 1 is e, so there's that point, and so on and so forth. So we generate this graph, and recall that the natural log and e to the x are inverses of each other. So these are inverse functions. That's why the yellow curve and the blue curve are symmetric about the line y is equal to x. They're symmetric about the diagonal, which means if I have a paper and I fold through this, through diagonal, these two curves will overlap each other because they're inverses of each other. So if I interchange the x and the y, so x is equal to e to the y, y would be the natural log of x because you're just interchanging ordered pairs. So if this ordered pair is 1e, this ordered pair becomes e1. Alright? Okay? Right, so because they're inverses of each other, that means e to the natural log of x is equal to x. Similarly, the natural log of e to the x, you get back x. Okay, so because of them being inverses of each other, you get back the argument, whatever your argument is. Okay, so now how about we take this last equation. Okay, so let's take the last equation, the natural log of e to the x equals x. Differentiate both sides. And what do we get? Well, we already know what the derivative of the natural log is, so we just apply chain rule. So if we differentiate both sides with respect to x, that's the argument of the natural log, so it's 1 over u, so it's ln u, so u is e to the x. Derivative of u, so it's the derivative of e to the x with respect to x. Okay? So that's equal to, what's the derivative of x with respect to x? That's 1. So multiply both sides by e to the x. And look what we get. Okay, you have the derivative of e to the x with respect to x is just e to the x. So that is just the coolest thing. That means that if I differentiate e to the x, I get e to the x again. So, which means that, alright, if we have u as a function of x, okay, and it's differentiable, of course. You can take its derivative, in other words. Alright, then what is the derivative of e to the u with respect to x? It's going to be e to the u by chain rule du by dx, because of what we derived here. So incidentally, then, that means it's if we want to reverse everything and take back the original function, the integral of e to the u du would just be e to the u. We're getting it back. Plus, of course, a constant. So these two things are just what we need to remember in 7.3 so that we can either take it, how do we find a derivative, at the same time how we integrate, if the integrand has a natural e, or if the function has a natural e, that's how we take a derivative and how we integrate. So just these two things are what's important to remember when we're in section 7.3. So let's go ahead and review a few properties of exponentials. Okay, this is just what we derived, okay, and that these two things, like I said. Also, if we have e to the x, if we have e to the x multiplied by e to the x sub 2, so e to the x sub 1 multiplied by e to the x sub 2, product of same basis, we add the exponents. Quotient, we take the difference of the exponents. E to the minus x, it's 1 over e to the x, and e to the x sub 1 raised to the r. This whole thing is raised to the r. You just multiply the exponent. So it's going to be e to the r times x sub 1. Right? I think we're ready to take derivatives, don't you think so? All right, so let's start with, say, number 5, right? So remember, the derivative of e to the u is just e to the u multiplied by the derivative of u. So y prime here is going to be, copy it, e to the minus 5x multiplied by the derivative of the argument, minus 5x, or minus 5. And rewriting it properly is just putting the constant in the front. So minus 5 e to the minus 5x. Okay, how about number 6? So let's do number 6. So in number 6 you have y prime would be e, copy it, 2x to the 2x over 3 multiplied by the derivative of 2x over 3, which is just 2/3. So rewriting it again, we have 2/3 e to the 2x over 3. Okay, and how about number 9? Number 7, I think you can handle that as well as number 8. So let's do number 9. We have y equals x times e to the x minus e to the x. All right, so what is y prime? So treat this as, since this is a product of x and e to the x, use product rule. So from product rule, so let me just write here PR. Product rule, this becomes, the derivative of the first is 1 multiplied by e to the x plus x times, what's the derivative of e to the x? Just e to the x. Minus, what's the derivative of e to the x? E to the x again. So you see that e to the x and a minus e to the x cancels out each other. So the derivative is just x times e to the x. There you go. Okay, let's see, how about we can do number 11. So let's do number 11. Number 11. All right, what's number 11? We have y equals x squared minus 2x, and then plus 2 multiplied by e to the x. So it's very similar to this one, what we're going to do here. So again, product rule. This is your first function multiplied by the second. So y prime equals, all right, 2x minus 2. Where did that come from? The derivative of the first times e to the x plus, just copy the first function, x squared minus 2x plus 2 times e to the x, because that's the derivative of e to the x. And if we factor out e to the x and combine all the x terms, we have 2x minus 2, right, plus x squared minus 2x, and then plus 2, pull out the e to the x. Okay, and do you see what we can cancel out? Cancel that out. What else? Right there. So what survives is just what is left is x squared e to the x. There you go. That's dy by dx. All right, so I think we have room for one more function. What I would like to do is really take the derivative of number 14. I think I would want to do number 14. So just so let's use a different color. So number 14. Right, we've got y, because it looks interesting because it's got a natural log. So the natural log of 3 times theta e to the minus theta. And I think since it's a natural log, I think the easiest would be to use the properties of natural log. Remember, when we have the natural log of a product, it's the sum of the factors, the natural log of the sum of the factors. So it's going to be the natural log of 3 plus the natural log of theta. Okay, and what do we have? We're lucky here. The natural log of e to the minus theta. And what did we say is the natural log of e to that something? This whole thing collapses. So we have the natural log of 3 plus the natural log of theta, okay, minus theta, because that's all that's left. Remember, because they're inverses of each other, okay? and we're ready. So we didn't even have to use the properties of, or the derivative function for for e to the theta. So dy by d theta is equal to, what's the derivative of a constant? Then it's 0. And then what's the derivative of natural log? 1 over theta minus 1. So there's your answer. It's going to be 1 over theta minus 1. So as you can see, all we did was use the properties of logarithm to make everything simple and then take the derivative. We didn't even use the fact that we have to take the derivative of e to the minus theta. So that's just cool. Now, suppose you just took the derivative to begin with. That will still work. It's just that you're going to have to work harder, but it will always simplify. It will still simplify to this expression. All right? So that sounds good. Let's keep going. Okay, I have number 21. I think I would like to do number 21. So in number 21, we have y is equal to, let me see, we've got e to the cosine t plus the natural log of t. Again, I would go about, well, you could either, write this as factors of e, or just take the derivative right now. So y prime, or dy by dt, okay, is equal to, just take e to its argument, cosine t plus natural log of t, multiplied by what? Okay, we take the derivative of whatever's the argument of e, so it's going to be minus sine t plus 1 over t. That's a derivative natural log of t. And there you go. So if you want to write, I think that should be okay. In fact, you can enter this as your answer. That sounds good. Okay, how about number 22? Let's do number 22. Y is equal to e to the sine t multiplied by the natural log of t squared plus 1. Okay. Again, if I have a natural log, I'm more likely to simplify that to make life easier. So this is going to be e to the sine t times, by the power rule on natural log, 2 times the natural log of t plus 1. Okay? So now you look at the big picture and say, what do I need to do here? Well, it's a product of e to the sine t and this sum. So I'll take the derivative of this first, multiplied by that, plus this times the derivative of the second function. So now we're ready to take the derivative. Dy by dt is equal to, just copy that, it's e to the sine t, and then chain rule, because what's the derivative of sine? Cosine t. Okay, so far that's what I did, multiplied by, I'll just write it in a different color, that way you'll see. 2 natural log of t plus 1, right? Plus, okay, what do we do now? Now we take the derivative of, so we copy this, just copy e to the sine t, multiplied by what? Now we take the derivative of the second function. So it's 2 over t, because 2 times the natural log of t, derivative is 1 over t, plus 0. I'm going to write that down, that way you'd know that, oh, what did I do? I took the derivative of this function. Okay, so the rest is just simplifying. So I think what we can do now is just to go ahead and pull out e to the sine t. Alright, and then what do we have? Well, we've got cosine t times 2 natural log of t plus cosine t. I'm just distributing that over here. Okay, plus 2 over t, and that's your final answer. Alrighty. Okay, so we're done. So that's dy by dt. Now I think we're ready to take integrals.